Hi everyone, I am Engineer Rolando Abini Jr. and I am assigned to the topic Richardson extrapolation and partial derivatives. To start, Richardson extrapolation can be used to estimate derivatives of a function and integration of a function. We all know that differentiation and integration are inversely related to each other. Richardson extrapolation is a combination of the trapezoidal rule. Its general equation is I is equal to H plus EH, where IH must stand to the trapezoidal rule. And this trapezoidal rule, it is the method in estimating the integral of a function. And truncation error, which estimates the derivatives of a function. So truncation error is part of a topic in chapter 4, which is already discussed by and covered by the midterm topic. So I will no longer be explaining this. So using Richardson extrapolation will give us a fourth degree of estimates, unlike truncation error, again, which is in chapter 4, which only up to second degree, which in this case, it gives us more accurate values. So this is the beauty of Richardson extrapolation. Unlike truncation error, it only, it's, since we are dealing with an estimation of an integration and differentiation, if we have a certain function, say we have a function, and then of course we can integrate that function and differentiate that function. So truncation error, it can only give a value of up to second degree, which is if we are going to project or estimate the true value of the function. So Richardson extrapolation is way more accurate than truncation error. Mathematical background. So this is the general equation for Richardson equation, extrapolation equation. So I is equal to I of H plus E of H, where I is the exact value of the integral. I of H is the approximation from an n-segment application of the trapezoidal rule. With step size, H is equal to B minus A over N. This H equals B minus A over N is the trapezoidal rule method, which I will be showing in the next slide. So, and E of H is the truncation error. If we make the two separate estimates using step sizes of H1 and H2 and have exact values for error, so our equation would lead us to I of H1 plus E of H1 must be equal to the I of H2 plus E of H2. Again, this H is the step size of the step size of the trapezoidal rule. So this is now the where the H came from. So actually it is called an trapezoidal rule because if this is our function, this one, this black curve. If this is our function, true value of our function, we don't know if what is that function, no? But if we plot the certain function in, and this is what it look like, its function when we plot it. So trapezoidal rule in the idea of integration in the integral calculus. So basically we are dividing this one. Say for example this one, we are dividing a certain area. If you can still remember the integration integral calculus, we always do or get a small strip, either dx or dy. It depends upon our where are we going to get that area. So in this case, this is called a trapezoidal rule. Of course, an integration is uh, we have a method in the integral calculus that uh, summation of, and we have the upper limit and lower limit. So in since a numerical method is again an estimating of the, for this certain topic is an estimating of the integration of the function, certain function. So this trapezoidal rule is meaning its method is by trapezoid. That is why it is called trapezoidal rule. If we can remember that the area of the trapezoid is equal to 1/2 times summation of bases. Say for example, base A1 and A2 times the height, shall we say H. That in this case, our H1, this must be our A1 or base 1, and this must be our base 2. So this portion here, the gap of x1 and x2 must be our height. So again, this is called a trapezoidal rule because basically its idea is to get the area of a trapezoid. He formed it as trapezoid and then calculate for the area of the trapezoid. Okay, next is recall that the error of the multiple application trapezoidal rule can be presented approximately by the following equation. So we have E is equal to B, negative B minus A over 12 H squared times F double prime. So this topic is uh, included in the report of my classmates. I will no longer be discussing this thoroughly because it is part of the report in the trapezoidal rule. I think this is this will be discussed by Engineer Acohido and Engineer Alvarez. So this is taken from still the book given to us by Chapra, Stephen Chapra. So with n is equal to b minus ah. So this is what I have shown earlier, the the trapezoidal rule. So actually that was in terms of h, but in this case it was just rearranged in terms of n. So anyway, the same equation still. So, and we have this term E of 1, E of H of 1 over E of H of 2. is equal to h of 1 squared over h of 2 squared. So by this relationship, we will going to arrive the same equation that was that we arrived earlier. So here, this equation e of h of 1, this one. So the same equation, we just cross multiply it and then set the equation in terms of h of e of h1. So if we can still remember the early equation that we have presented, like it was assumed that if we have h1 and h2, and this h1 and h2 is the step size of the trapezoidal rule, it will be equated. No, if I is I h of 1 plus e h of 1 must be equal to I h of 2 plus e of h sub 2. So with this equation, just substitute this value of e of h of 1 to here. So this would lead us to this equation now. And then our equation, so after substituting, we can arrive in this. Actually, this equation is just a rearrange of the early equation. So this is that was just rearranged, this one. So it is in terms the in terms of h of h e of h2. So this one is transposed to the other side, and then this one to the other side. So this is just the continuation of the equation. So and then it combined the terms of e of h of 2. Substituting again in the truncation error, so to our general equation of the Richardson extrapolation, we have this equation I is equal to I of h2 plus e of h2, as simply substituting again this value e of h2, this one, to our general equation that I have presented, the first formula that I presented. So just substitute this whole value here to here. So we can get this equation, no? This one, this equation. Or this one. Or because this is just algebraic manipulation. So if we factor a -1 here, so of course the sign of this one must change. This must become positive, and this one here must become negative. So it will lead us to the sequence, and then the same at bottom, we factor -1 here, so that sequence would reverse. So and then since -1 divided by -1, still this is positive. So basically the arrangement of the terms was just the arranged but the same equation. So this is our equation now. And then for the special case where interval is half, so h sub 2 must be equal to h sub 1 over 2. So h2 is half. So this is a special case. So our equation, our equation would lead us to this equation, because if we substitute h of 2 this here, this will become h of 1, uh, h of 1 over 2. So of course, this is the same term, so ma-cancel siya, and then this would lead to I of h sub 2 plus copy the upper term. So this is minus of h sub 1 all over, since h1, this 2 here is can be inverse, so it would lead to 2 squared minus 1, or this is just 4. So minus 1, this whole denominator here will become just 3. So by algebraic manipulation, so by least common denominator, we are going to uh, get the least common denominator. So we will multiply the 3 in the upper of this right. So this will become 3 times h of 2 plus I of h of 2. Still copy this right side upper terms. So I of h of 1. So same, this is the same term. I of h sub 2. So this will become 4i h sub 2 minus I of h sub 1, still over 3. So we can now arrive to this. He just separately divide the two terms by 3. So the right side becomes 4/3, and then the left side minus 1/3. So, and this is now, this one here, this is now our equation for the Richardson extrapolation. Okay, so say for example, so this is the example given to us in the book. So using the same function as in example 23.1, so estimate the first derivative at x is equal to 0.5, employing step sizes of h1 is equal to 0.5 and h2 is equal to 0.25. Then use the equation 23.8, the one that we have derived earlier. So to compute an improved estimate with Richardson extrapolation, recall that the true value is negative 0.9125. By the way, since this example is already solved in the earlier example, this is already example 23.2, and it was solved in example 23.1. So what I did is I just copied the original equation. So in order for us to solve this specific problem, so we need to also know all the details. Now, in example 23.1, it state that, recall that in example 4.4, we have a function of negative 0.1 x to the fourth minus 0.15 x cubed minus 0.5 x squared minus 0.25 x plus 1.2. So this, I won't be discussing this in detail because still this is a cover of my classmate, topic of my classmate. I think that is Engineer Daos and Engineer Derecho. So I just want to show this because this is related to the problem solved. problem that was assigned in my topic under Richardson extrapolation. So he computed in high accuracy differentiation. He uh, computed the forward difference. We have the forward difference value, backward difference, and centered difference. Now, this forward, backward, and centered difference still is already discussed on the topic truncation error. So there is a topic there, numerical differentiation. So this whole equation, this is a derived equation, forward difference, backward difference, and center difference. And it was based on the Taylor series. So anyway, this is not my topic. So I just want to show and to give background what are these terms are, and then next, so I did copied also the value, the original problem that was quoted in example 23.2 and 23.1. So this is the original problem, and it was solved by the finite difference approximation of derivatives. This is still in chapter 4 under the topic of the midterm. So use the forward. This is the original problem actually. Use the forward and backward difference approximation with O of H and a center difference approximation of O of H squared to estimate the first derivative. So this is the function, and then the given is we have X is equal to 0.5 using step size. H is equal to 0.5, and then repeat the computation using H is equal to 0.25. So again, this is not my topic, but I will just give background for this example. So this is for H of is equal to 0.5. So he derived these values here. And if we are going uh, to follow the process, so he arrived this uh, given given this x sub I, no, this x here that was given in the problem, this is assumed to be the x sub I since this is differentiation or and integration. Say for example, the earlier curve that we have. So we are dealing with if you can observe na it's sub-zero last time itong di-discuss na ako. This is x of I minus 1, and then here in the trapezoidal rule, so the labeling of the points here in x-axis is in terms of x of I, and then x of x1 minus I mean I minus 1, and then I plus 1. So since we have a value of this 0.5, so and our h here, so still the h here is the gap this of x of I and x of I minus 1, and the same h must be equal the gap of the x sub I and the x sub I plus 1. So that is why he arrived at the value of 0 and 1 for x sub I minus 1 and x sub I plus 1. And then if we substitute this value 0 to our function here, this one, this x here. So of course, the function of x of sub I minus 1 will become to 1.2. Because if this is 0, this is 0, this is 0, This is 0. So of course, what is left is just this 1.1, 1.2. So the same principle applied in getting the function of this f of x sub I, which is he derived of arrive of the value of 0.925, and then for f of x plus 1, 0.2. Because this is the main problem, the source of the problem that I am going uh, to discuss. So at least I have already this data. So for h, that was for h, step size h is equal to 0.5, and then for the value, he calculated again the forward difference, backward difference, and then center difference. And if you can observe the values of the backward difference, forward and backward difference is almost is accurate than the center difference here, calculated here. And for step size, h is equal to 0.25, still the same function that we are going to use, and then substitute the value of the 0.25 to our function. We will arrive the value of this one. Can I substitute this to our function, given function, and then the same, so we will arrive. So I will just copy this calculated values here for the solving of the Richardson extrapolation. So this is the backward difference and the center difference. For h is equal to 0.25. For both step sizes, the center difference approximation is more accurate than forward and backward differences, also as predicted by the Taylor series. So this is maybe because for the h is equal to 0.5, the values of forward and backward difference is negative. So no, the more accurate pala is the center difference, because the error for uh forward and backward difference is 58.9 and 39.7 respectively, while for the center difference is just 9.6%. So I was mistaken earlier. So anyway, this is the sample problem that I have. So I already copied. I just copied the values given at the function given. This one, f of x, this one. So I just copied it to for me to is here in the also. I also copied the values that was computed. So this one here. So still this is the derived. Actually, this is the derived extrapolation, Richardson extrapolation formula that we derived earlier, and then the function, given function. So this is the computed values in that example 4.4 for h is equal to 0.5 and for h is equal to 0.25. So the graph here at the right side is the graphical depiction of a forward and backward difference. So again, that this is the point that I pointed out last time, the x sub I, and then this is must be the x sub I minus 1, and this here x sub I plus 1. So still this is the same h here. Anyway, we already have a values for it was already solved in the earlier example. So using the same function as in 23.1, estimate the first derivative. We have a given x is equal to 0.5. Exploring step sizes. So we have the given h sub 1 is equal to 0.5, and then h of 2 is 0.25. So to compute an improved estimate with the Richardson extrapolation, so recall the true value. So this is the value calculated for the step size 0.25. It was shown earlier, this one, 0.9125. So the example of 23 points. So this was calculated in the example 23.1. So solution, the first derivative estimates can be computed with the center difference as this one. So the equation of this is since this is a center difference, the value of center difference is just the function of x of I plus 1 minus the function of x sub I minus 1 over x of I plus 1 minus x of I minus 1. And we have the values of that here for f of uh, x sub I minus 1, we have 1.2. So this one, 1.2. And then for x sub I plus 1, we have 0.2. So just substitute the values here, 0.2 and 1.2. And then for uh, x sub I plus 1 minus, which is the values 1, and then minus the x sub I minus 1, which is the value is 0. So that is 0. I mean 1. Difference of these two is just 1 here. So this is for the h is equal to h1, 0.5. This is the values. So for h of 2, he denoted here as d of 0.25, which is this is the step size 2, which is 0.25. So the value still is this one. We have the value for x sub I minus 1, 1.1, blah, blah, blah. And for f of x I sub plus 1, this one 0.63, and so on. And the corresponding value of x sub I minus 1, 1.25, and 0.75. So that was just copied here, this one and this one for the upper. And then for the difference in the bottom, which is 0.75 minus 0.25. So we have a value of 0.5. So we have a value of an error 0.9.6 and negative 2.4. I remember earlier that the values that was computed in the example 4.4, the most accurate among the three values in the forward, backward, and center difference the center difference is the most accurate values for the step size 0.5 and 0.25. And that's why we have also solved the values for the center difference here for us to see when we calculate now for the value of the by using Richardson extrapolation. So these are the value for the center difference. So by using the Richardson extrapolation, again, our equation is this one. By the way, maybe you uh, are wondering why this is D and this our derived equation is I. So the idea there is that since this we are dealing with the derivatives here, so since kaninga topic is more on derivatives siya, and then katong sa Romberg, more on sa integration siya nga part, but still we can use this Richardson extrapolation in estimating the true value of the function. So that is why it is replaced the I with D. So anyway, same equation here. The I of h of 2 is replaced by D of h of 2, where the D of h of 2 is h of 2 is 0.25, this one. So we have the value of uh, 0.93. Just no, this one here. The D of, since these values here, this one, these values here, this is D of 0.25, this one. So this is the derived from the center difference 0.934375, which is our D of H sub 2. And then for D H of H sub 1, so this is the value -1. Therefore, what we have calculated is negative 0.9125, and this is the true value which is also given. Actually, this is solved in example 23.1 using the high accuracy differentiation formulas that I have shown earlier. So this the same with the high accuracy, Richard extrapolation is one of the method in estimating. With the same with high accuracy, Richardson extrapolation result is also accurate. So that's all for the Richardson. Next topic will be the partial derivative. So partial derivative along a single dimension are computed in the same fashion as ordinary derivatives. For example, suppose that we want to determine the partial derivatives of two-dimensional function f of x, y. For equally spaced data, the partial derivative can be approximated with the center difference. So this is the value of, actually a value of center difference, these two equation here. The partial derivatives, it is denoted as this one, the sign partial, that if we are going to use this, that means this certain Greek alphabet, it means that we are differentiating partially. So from the word itself, partial derivatives, no, partially, derivating partially. So we can differentiate if we have a function of x and y, we can just derive, differentiate all the function in terms of x, and the same goes with differentiate just the function of y. So we can use this. This is uh, the function of these partial derivatives. Next will be, okay, for mixed partial derivatives, we can also differentiate both, no, for this one, we can differentiate separately. Differentiate the function with respect to x and separately differentiate the function with respect to y. But for mixed partial derivatives, we can differentiate the function with respect to x first and then with respect to y uh, in the same function. So this is called the mixed partial derivatives. And then for the mixed partial derivatives, if this is our equation, the center difference, then this would lead to this equation, the partial squared of f over partial of x times the partial of y is equal to the partial derivative of f with respect to y of the function x plus delta x of y minus partial derivative of f with respect to y of the function x minus delta x plus y all over 2 delta x. Again, this is just but this one. No? The first term here, and then we differentiate both with respect to y. And then copy the denominator to delta x. So, if we are going to uh, we are going to initiate or in what you call this one, differentiate this one, the basis for derivatives, say for example, di ba, we have, say we have y is equal function of x. Now, what we will do in the differentiation basically is we will add a delta y to the right, and we will add 4x delta x. So this is the method based on also on the dictionary, the definition of the derivative, which is the rate of change of the dependent variable and independent variable. So what will happen here basically is sub transpose na to ang y to the right, so that in the left side will be in terms of delta y, and we know that delta is derivative or change. So expressing it with respect to delta y, still copy we have the function of x plus delta x and then minus y, because we have transported a value y here. And then if we are going to substitute the value for y, which is the function of x, therefore our equation would become f of x plus delta x minus, this must be a function of x. So by the law of algebra, what you're going to do in the left side you must do also on the right. So to get the value of derivative, so we know that the derivative is we have a dependent and independent variable. So we must differentiate y with respect to x. So we need to divide delta x in the left side and also delta x in the right side. And this is the actually the definition of the derivative. No, delta y over delta x, or the differential of y with respect to x. If we have a function of x, so this must be f of x plus delta x minus f of x over delta x. So this is our uh, mathematical expression of differentiation. Now the same happen here. Since we partially differentiate this function, our function is this one. So the same goes. So if our function is equal to the function of x plus delta x of y and y, so same here, we need to add a delta value. So we need to add in the left plus delta f to get this delta or differential but term for f. It must be equals to f here in the right. So since we are dealing with only y, so we cannot add a delta x, and also there is already a delta x in the x side. Now we are after of the variable y because we are differentiating with respect to y. So therefore, we must add a delta y here for our function. And the same principle, this function f must be uh, transposed it to the right side. So our equation now will become delta f is equal to function of x plus delta x, and then y plus delta y minus f, since we again transpose the f here. And then if we are going to substitute again the value of f here, which is this one, then our function will become x plus delta x, and then y plus delta y minus the function of x plus delta x and y. And then since we are after with respect to x, so we will divide both sides by delta y, and here by delta y, and that is now the outcome. If you can observe, this term, whole term here, is this one. So, and then the same goes with this, the right side here. The same goes, the same sequence, but the our function is now not plus, but this must be a negative, and the same process, and then we will arrive at this equation here, this one. So this right side, left side here is the partial of f with respect to y, the function of x plus delta x and y. This whole term here, this one. And then for their right side, same partial with respect to y over function x minus delta x of y. So this also is the whole term here. Now, by common denominators and same sa siya, same ang iyahang base. So we can just minus. So if you can observe, nag-minus lang ta for this one here. And then nag-minus po ta diri sa this must be, yeah. And then, and the denominator basically will become 4 delta x and delta y. So this now is our equation for the mixed partial derivatives. And that's all for my presentation. I hope you learned something. Thank you for listening and may God bless us all.